Welcome to The Explainer. Listen, today we're treating the Cambridge AS and A-level computer science syllabus not like a textbook, but like an optimizable system. An e-sport, if you will. We are executing a high-stakes, strategic speed run of one of the absolute most critical frameworks in the entire curriculum, converting integer values between number bases. Now, our objective today is incredibly simple but absolutely crucial. We are going to maximize your marks per minute by totally eliminating wasted actions when you're dealing with binary, denary, and hexadecimal. We need to accelerate your performance. We're going to deploy rapid, highly accurate frameworks, and you'll understand exactly how to conquer these foundational questions before the exam timer hits zero. Let's break down the optimal routing to outpace the clock, avoid the common traps, and demonstrate absolute technical mastery to the examiner.
Right off the bat, let's talk stakes. A senior examiner recently noted that the difference between a B and an A-star grade often comes down to this specific topic. Why? Because this isn't just about doing simple arithmetic. It is literally the ultimate gatekeeper of the syllabus. It tests the absolute foundational principles of computing. Look, examiners use base conversion questions to separate the candidates who have just superficially memorized a textbook from the elite candidates who possess a deeply connected conceptual understanding of data representation. If your method here is slow or kind of flawed, you lose critical momentum that you desperately need for the rest of the paper. We need to build a logical, analytical approach right onto the page to maximize your score and keep your mark velocity tracking at 100%.
All right, let's jump straight into Section 1, Core Mechanics and Analytical Depth.
Okay, consider two different players, let's call them player 1 Alex and player 2 Sam, and how they approach these exam questions. Alex relies on the superficial approach. He's just trying to memorize basic binary place values. But the second he's faced with a complex 2's complement question, his run completely stalls out. He wastes massive amounts of time and struggles to actually articulate the mechanics. Now look at Sam. Sam uses an analytical approach based on structured reasoning. Sam understands exactly why the most significant bit acts as a negative sign. This deeper conceptual link allows for instant, high-velocity problem solving. The Cambridge syllabus explicitly points out that top-performing students demonstrate mastery of these fundamental principles so they can apply them effortlessly to completely unfamiliar contexts. Sam throws down a high-velocity breakdown that clears the mark scheme checkpoints instantly, while Alex is left staring at the clock. We want you playing like Sam.
Moving right along to Section 2, the optimal procedural route. Here is your exact step-by-step procedural framework, your combo sequence for tackling literally any conversion they throw at you. Step 1. Identify key elements. Extract the given integer from its binary, denary, or hexadecimal representation. Read the prompt carefully. Step 2. Apply relevant principles. Select the correct place values. You have to ask yourself, are you using an 8-bit or a 16-bit register? Is this unsigned, or is it sign in magnitude? Step 3. Execute the analysis with clear, visible working. This is your step-by-step grouping of bits or your repeated division by 16 for hex. Do not skip this. Step 4. Verify your results. Do a quick sanity check for reasonableness. Maybe even convert it back to the original base really quickly just to test your output. And finally, Step 5, present it in the appropriate format. If the question specifies an 8-bit format, you better make sure those leading zeros are included. Deconstruct, solve, and evaluate.
Which brings us perfectly to Section 3, Securing Your Method Marks. Time split check. Before we execute this next high-value concept and lock in an A-star grade velocity, you need to optimize your own study feed. Subscribe to Ace the Exams. That's at ace-the exams right now and turn on all notifications. No matter if you're running IGCSE, O-levels, AS, or A-levels, this channel is your tracking center to outpace the clock and beat the examiners. Okay, back to the run. Even top-tier candidates hit structural roadblocks during high-pressure exams. The difference is how you handle it. Let's compare a flawed run against an optimized run. A candidate moving way too fast might just write down a final binary string after doing all the math in their head to save time. But here's the catch. If a single bit in that string is wrong, they get a 0. It's a totally flawed approach. An optimized run, on the other hand, moves deliberately. It shows step-by-step decomposition. By writing out your binary groupings, the powers of 2, or the bit shifting required, you are actively securing method marks for the process itself. Even if your final calculation is slightly off because you rushed the addition, an optimized candidate secures their grade through visible, logical steps.
I cannot stress this enough. This is a critical developer patch note straight from the principal examiner reports. Students lose massive amounts of marks by not showing their working. Even if your final base conversion is dead wrong because of a tiny, simple arithmetic error, writing out your binary groupings step by step secures method marks. Your working out is your ultimate safety net. It's your extra life.
When you hit a complex denary to hexadecimal conversion, please do not try to be a hero and solve the whole thing mentally. Write down the intermediate binary conversion first. Divide that binary into 4-bit nibbles. Translate each nibble into hex. Create a pristine, high-scoring block of evidence for the examiner to literally throw marks at.
Let's keep the pace up. Section 4. Spotting performance leaks. Now we're getting into the higher-order assessment objectives. These demand that you don't just calculate, but evaluate alternatives and justify exactly why certain data representations are used in the real world. When you're asked to evaluate representation quality, you must understand the practical impact. For instance, why on earth do we use hexadecimal for memory dumps instead of binary? A lot of students say, oh, the computer processes it faster. No, it absolutely doesn't. The computer only reads binary. Hexadecimal is used because it takes up significantly less space on the screen, and it's infinitely easier for human programmers to read, which drastically reduces the chance of transcription errors. That is the key. You also need to evaluate the hard limits of an 8-bit integer versus a 16-bit integer, knowing exactly what the maximum and minimum representable values are. Spotting these performance leaks and evaluating the impact of these limits is exactly how you clear the top-tier mark checkpoints.
Almost at the finish line. Section 5. The examiner warnings. Let's rapid fire through the top 3 fatal errors documented in Cambridge Examiner reports. These are the traps that will instantly tank your run. Number 1, students constantly forget to check for overflow. Overflow happens when a calculation produces a result that requires more bits than your available register size, like adding 2 8-bit numbers, hitting 256, and boom, the system rolls over and you've lost data. You have to check for that. Number 2, ignoring boundary conditions. Failing to realize that a choose complement 8-bit register can only represent values down to -128 is a classic run killer. And number 3, providing generic textbook answers that are not specific to the context given in the prompt. If the question specifically asks you about a robotic control system's registers, your answer has to reference that exact robotic system. Don't just spit out a generic definition of binary. So how do we combat these traps? You need a fast, deployable tool for your final 5-minute review pass. We highly recommend creating a memory hack, a mnemonic device utilizing the first letters of key terms. Try using OBCE, which stands for Overflow, Boundaries, Context, and Edge Cases. Just memorize OBCE. During the final countdown of your exam, run this mental checklist over every single base conversion you did. Check the math. Has any overflow occurred? Verify the boundaries. Does the result actually fit in the specified bit length? Check the context. Do your written explanations actually match the prompt's specific scenario? This systematic review is exactly how you lock down a pristine paper and capture those easily missed marks right before time is up. So, as we complete this framework run, I want you to look at your own process. Which step is leaking the most marks for you? Is it superficial memorization? Are you refusing to show you're working out? Or are you forgetting to check edge cases like overflow? Master the mechanics of base conversions, and you don't just pass an exam, you literally learn to speak the native language of the machine. Next time you look at a string of ones and zeros, ask yourself, are you just reading numbers, or are you seeing the architecture? Keep optimizing your approach. All right, time to lock in your final score. Make sure you subscribe to Ace the Exams, that's at Ace the Exams. Click the notification bell for more weekly speedrun tutorials and drop a comment below sharing which specific Cambridge Unit framework you find the hardest to clear under time pressure. Keep your velocity up, and I'll see you in the next explainer.